Hello everyone. So I've got a case history. The case history this time is going to be the Eiffel Tower in Paris, and then we'll come back and talk about Atterberg limits, and we'll start classification of soils. So let me get the lights and then talk to you about the Eiffel Tower. Let's see if I can bring up my pointer, laser, there we go. So the Eiffel Tower was built in 1889 for the World Fair, and these are the two major sources of information I used. So here is the tower. It's known worldwide, and but very few people know about the foundation of the Eiffel Tower. So I want to talk to you about the foundation of the Eiffel Tower. It's interesting yet not dramatic, because everything went well, and so there's not much to talk about except to let you know what it's made of. So the Eiffel Tower, you know, people get excited about this tower. You know, you might think, well, it's just a big drill rig. I mean, it looks like an oil rig, but it's one of the things I've found that when it comes to historical monuments is that those who last through the years are those that have shapes that are remarkably simple and elegant. And I think that's one of the trademarks of this tower. It's the shape itself is remarkably simple and elegant. So you can actually walk from you know, take the stairs to this first activity level here. You can also continue to take the stairs to the second level. This is a very expensive restaurant. So if you're gonna go there, you need to make a reservation probably about 6 months to a year in advance, and then make sure you save your pennies for a good while, because it's probably going to be about $250 per person. And then you cannot walk to the third level, but you can take an elevator, actually an elevator that starts all the way from the bottom here, but you change elevator to get to the very top of the tower. And a little side story, I met my wife Janet in 1972, and in '73, so I met her in Canada, and I thought, well, next summer I'll go back to France and show her a number of things, including the Eiffel Tower. So she was pretty impressed, except when we took the elevator going up from the second level to the third level, the elevator got stuck right in the middle, and we had to finish on battery. So I was trying to impress her, but I didn't do too well. Anyway, so seriously now. Here's the foundation of the tower. So we're very close to the Seine River, and we have 4 supports, pier 1, 2, 3, 4, and each support is on a group of 4 individual piers that are about, you see on this side, about 13 meters deep. And on this side, so the river is on this side here, so as you get closer to the river, the soil is softer, and so the foundations of this pier had to be deeper than the foundation of this pier, which is away from the river. So here is the view, the plan view. Here's the river right here. This is about 200 meters, and the Eiffel Tower itself is about 100 by 100 meter. You have pier 1, 2, 3, 4, and each pier is made of these 4 individual blocks that go down close to the rock support. So here is the soil. You have sandy clay here, and you have limestone at this level, and the limestone rises, sand and gravel right here. So the foundation engineers tried to stay away from that sandy clay, which was softer, sandy clay deposited by the river over time, and then the sand and gravel was a much stronger foundation, and so that's where they placed the foundation itself. So here's a cross-section. You have the river sand on this side, the retaining wall, and this is fill of various kinds. Then you have the sand and clay right here, sand and gravel layer that starts to thicken as you get away from the river, and then underneath that the bedrock. So these are more cross sections. These are the large openings that were done to be able to find out what the soil was as a function of depth. Here's a plan view of one of the 4 supports, and you can see these 4 elements that are going to be supporting one pier of the tower. Here's another one, another one, another one, and here they are being constructed, and you can see there's one right here, one right here, one there, and one there. And these are steel cans, if you wish, because the river being close, there was enough water that through the excavation of the foundation, the water would come into the excavation. And so they had to operate under air pressure to excavate the foundation by hand. 1889, so we don't have big drill rigs and excavators and dozers and equipment like this at the time. So these are, and I think there's another picture, yeah, so here is one of those cans. You see the people right there, the size, and 1, 2, 3, and 4, and the ladder so that people can go down, and then once they're in there, they close the hatch of that container, pressurize the inside so that the water cannot come into the excavation, and then they continue to excavate under those conditions. So people working under pressure, and you can see that the material is coming up, and the anchors that will tie to the steel structure of the tower. Here are the 4 blocks of one corner, 1, 2, 3, 4. And here's how the anchor connection will be. Here's the foundation block, and here's the first leg of one of the corners. Connections as well. All these are drawings from this book, like the top left here, Briaud 2006, that collected. And so here's the beginning of the construction. This is one pier, and again, 1, 2, 3, and 4 of the connections to one corner. December 1887, March 1888, and June 88, August 88, February 89, May 89, ready in time for the welfare. And it's amazing. I mean, that construction, you see these workers here, and today we have OSHA, and there's no way that this would have been acceptable, because these workers have no tie to the structure, so that if they fall off, they go down 300 meters, 1,000 feet. And look at this, they seem to be comfortable. It's amazing. Every time I see that picture, and so here's the gradual construction of the tower. Now, I want to take a few minutes here and take you for a visit of Paris. I spent 3 years in Paris as a student, and if you look at this, I was right here in this part of town. That's the student quarters. So Notre Dame is here, the big cathedral that burned a year ago, 2 years ago. This is the river that crosses. It flows from this side to that side and goes all the way to the channel. The Eiffel Tower is here. The Arc de Triomphe is here. Le Louvre is there. And so we're gonna, I want to show, we're gonna be sitting here looking this way. And this is a, let me get rid of this thing, pointer option. I never know how to get, I don't know how to get rid of this. Let me enter, maybe, no. All right, back, here we go. Maybe I'll do it this way. Boom. Yeah, I think it's gonna work. So this is Air Panel. You may want to write this down because it's a cool website. And you can go all over the world and travel. So as I said, we're looking, here's the Arc de Triomphe, here's the Eiffel Tower. I love that music. I don't know about you, but when I hear that music, I feel like dancing. Anyway, so this is the river right here. And I don't know, but when the Tour de France is some of you may be cyclists. So the Tour de France comes in here, goes around the Arc de Triomphe, down the Champs-Élysées, comes around, and in front of the Louvre, Rivoli, back to Place de la Concorde, and up there, that's the finish line. Here is La Madeleine, the temple. This is Place Vendôme, jewelry. If you go there, what do you think? It's expensive. Many zeros. The opera, beautiful structure, beautiful structure. And then we're going to come around. This is right here is Montmartre. So Montmartre is a big hill. This is the highest point in Paris. So if you go there and you look this way, you will be on the high point, and there's some really cool restaurants on top of that hill up there. Anyway, I think if you can, here we go. So as we turn, we see the other side. So this is the Louvre, and if I turn a little bit more, should be able to see Notre Dame. I don't see it here, but it's here somewhere. Oh, here it is. Yeah, you can see it. Oh well, we lost it. So Notre Dame was in the background. Anyway, enough of that. So Air Panel is a cool, let me put the lights back on. So really, and you can go to Hong Kong, Rio de Janeiro. You can go to all kinds of places. So if you don't have the money to go in an airplane and do that, you can get with friends and travel in that fashion. It's pretty cool. I discovered that, and I thought I'd share that with you. Okay, down back to Earth. Let's talk about Atterberg limits. So let me write this here. Let me turn off that thing over there. Right. So Atterberg limits. So Atterberg limits are, first of all, Atterberg was a Swedish scientist who worked in agricultural engineering. And around 1910, he developed these limits of consistency. You know, we've talked about the fact that the larger particles, the gravel and sand particle, behave because of their weight. This is what dominates the behavior of these larger particles. But when you go to the finer silt particles, and certainly the clay particles, their weight becomes negligible. But the way they interact with each other, so these electrical forces that I mentioned in the last lecture, become very important. And so instead of finding out, we still find out their sizes through the hydrometer analysis, but that's not what's so critically important. The way they behave once they're together is more important. And so we have to find ways to measure this, this behavior of this consistency, how sticky the material is, how well it behaves when you work with it. And that's what Atterberg did in 1910. And you will see as we talk about those limits, they are remarkably simple. So simple that they look unscientific, unimpressive, and many people say, oh my goodness, surely we can do better than this. 110 years later, we're still using Atterberg limits. And why? Because they're simple, they're inexpensive, and they're very useful. And if you really want to you know, develop something that, that will be very successful, these are three things that are critically important. You know, if you start in your business or you want to develop a new trick, a new device, make sure it is simple, inexpensive, and very useful. And that's what makes the Atterberg limits very hard to replace. So what are they? Well, number one, Atterberg limits are water contents. Okay, they're water contents that have a special meaning, special definition. They are performed on remolded soil. So they're not intact soil behavior. You start by remolding the soil, and then you see how it behaves in this fashion. Let me make a drawing of water content. So here we're going to put the water content on the vertical axis. And here I'm going to put, did I do this right? Yeah. So here we're going to put the volume of the material. And so at first you take the clay and you thoroughly mix it with water. And it's very soupy because you added a lot of water to the clay. So at first you have a very high water content and a large volume. So you're over here. And then you let the material sit in place, and it's going to shrink. It's going to shrink and it's going to harden. And as it shrinks and it hardens, the particles are coming closer and closer and closer together. And there's a point where they cannot get closer together because they're touching each other. But you can still lose water from within the pore. And so you can continue to lose water content decreases, but you no longer lose volume. So what happens is this goes straight down. Now this is an approximation, but so at this point right here, we have what is called the shrinkage limit. WSH, the shrinkage limit. And then there are different levels of consistency. Right here we will find the plastic limit, WP, and here we will find the liquid limit, WL. And what Atterberg did, he defined where this was, where this was, where this was, arbitrarily. Okay, he made a decision, he wrote it up, people thought, oh, this is pretty cool stuff. They've been using it ever since, and it works quite well, as I will explain later. So, these limits define different states of consistency of the material. So above the liquid limit, the material is liquid. What does that mean? Well, it's not like you can pour it, but it's like toothpaste. So it's very soft, toothpaste consistency. Between the liquid limit and the plastic limit, the material is in a plastic state. So this is plastic. And what does that mean? Well, it's like soft caramel type of consistency. All right, soft caramel. And then between the plastic limit and the shrinkage limit, you have a semi-solid state that, right there, semi-solid state, which is like hard chocolate. This sounds like good food, but don't eat the sort. And then below that you have solid state, and this would be like peanut brittle. All right? So these are different consistencies of the soil, and between these consistency domains are the liquid limit, the plastic limit, and the shrinkage limit. So how did Atterberg define those? Well, he developed some tests that you are doing in the lab, and that I want to go over it briefly here, because you're going to go through the details of these tests. First of all, let's talk about the liquid limit. So remember, the liquid limit is a water content. It's a water content on the remolded soil at a state that's pretty soft. The liquid limit, in short, I'll just say that is the water content at which the remolded soil behaves like a soft paste. Okay, like I say, toothpaste, so you have a sense of what the material is like. Now, there is an ASTM standard. You know, ASTM is the American Society for Testing and Materials, been around a long time, and they standardize a lot of things. It's amazing. They standardize soil tests, they standardize rubber testing for tires, they standardize deodorants, they standardize all sorts of things. There's about 150,000 members of ASTM, and it's very difficult to get a standard to go through ASTM Why? Because the 150,000 members all have to agree on that standard. And so if you're a member of ASTM, you receive those standards about things you don't know anything about, and you have to approve. So of course I abstain when I get those things because I have no idea what that is. So it's a remarkable, and it's made of people like you and I, you know, practitioners, professionals, so very, very strong organization. And that's why they, it's always when you run tests in civil engineering, did you follow the ASTM standard? It's very important to pull the standard out, read the standard, and follow the standard as you run your test. So the ASTM standard says this exactly. I'll read it to you. Liquid limit is defined as the water content at which the two sides of a small amount of soil placed in a standard cup and grooved by a standard tool will flow together over a distance of 12.5 millimeters when hit by 25 blows in the standard liquid limit apparatus. Wow. And you're doing that, you know, you will see the little cup, and you put a pad of soil in there, you make a groove in the center, and this is reticulated soft paste, and then you provide blows, and when you turn the crank, it lifts the cup, and at one point, boop, it drops the cup, so bang, 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 and you have to make sure these two sides of the cup, of the soil pad are coming together over a distance of 12.5 millimeters at 25 blows. So chances are it's very difficult to hit it in that. So if, for example, you get these 12.5 millimeters at 10 blows, well, that means the material is too wet. The water content is too high, it's higher than the liquid limit. And if you hit the 12.5 millimeter touching length of these two sides at 40 blows, that means the material is too dry. So then, you know, and you can plot, you don't have to hit it exactly on 25, but you plot the points and you can calculate what, when your water content corresponds to 25 blows. So it's, you know, a little bit time consuming, but within 15-20 minutes you should be able to get that. One of the things that is notable is that WL will be much higher for very fine particles. For example, you remember Montmorillonite? WL can be definitely larger than 100%. 100% water content. That doesn't mean the whole thing is water. Remember, because it's weight of water or weight of solid. Please don't make that mistake on the midterm. That will be a question. What is the water content? Weight of water over weight of solids. So Montmorillonite would have, if you had kaolinite, for example, then probably the liquid limit is going to be lower than 40% or so. Approximate things. And so that gives you an indication of these sorts of things. The second limit is the plastic limit. WP. So the plastic limit is drier than the liquid limit, and it is in short, it's the where the remolded soil. So we'll write it the same way: water content at which the remolded soil behaves like a, let's see, what did I put? Behaves like a hard paste. Okay. Again, this is a rough definition so that you get a sense of the consistency of the material at that point. But there is an ASTM definition, a precise one, and I'll read it to you. The plastic limit is the water content at which a soil will begin to crumble when rolled into a thread 3.2 millimeter in diameter. So 3.2 millimeter in diameter. The difference, so we'll begin to crumble. So how do you do the test? Well, you have a glass plate, and you take the remolded material, and then you roll it in little threads. Not very complicated material test. So you roll it in little threads, and if it starts to crumble when it's 10 millimeters in diameter, the material is too dry. So it's below the plastic limit. If you roll it and it's very wet, and you can roll it down to 1 millimeter, when it starts to crumble, the material is too wet. So you need to let it dry, and then now that one you have to hit it on the nose. You have to get it down to, it's 1/8 of an inch, okay? That's why it's 3.2 millimeters. When it comes to 3.2 millimeters, then, and it crumbles, then you take the pieces, put it in your water content container, and then you dry it and get the water content, and that gives you the plastic limit. And it's, again, we're going to talk about the value of these limits and why we have to go through this, which is not too glamorous. The last one is the shrinkage limit. And then water content at which the remolded soil behaves like, and let's see what I just said here. Well, we say like a semi-solid. But more precisely, it's the water content, so W, let me write it below, W corresponding to filling all the pores, all the voids of the dry soil with water. So if you think of the dry soil where you have solids and air, that's the dry soil, the phase diagram for the dry soil. If you fill all this with water, okay, so if you now make this water, then you're going to have weight of water, you're going to have weight of solids, and this ratio will be the shrinkage limit. But you have to start with the dry soil. So a problem could be a dry soil has a a unit weight of 15 kilonewtons per cubic meter. The porosity is 40%. Calculate the shrinkage limit. So you got to do the phase diagram, and you've got to find out how much volume you have of air, and then you have volume of air times unit weight of water. That will give you the weight of water that it takes to fill those voids with water, divided by the weight of solids, and that gives you the water content that corresponds to the shrinkage limit. Okay, so these are the shrinkage limits, plastic limits, and liquid limit. And there are a number of, I think I have room to put it on this side, a number of parameters that will be very useful to us in practice of geotechnical engineering. One of them, we've already defined D60, which is the particle size corresponding to 60% finer. We've defined the coefficient of uniformity, D60 over D10. We've defined the coefficient of curvature, D30 squared over D60 D10. That was for the grain size curve. Wait a minute, drawing for you this way. And now we have some parameters associated with the Atterberg limits. The first one is the PI, also often put I sub P, and that is the plasticity index. There is another one called the, so plasticity index, what is it? It's the difference. It's the difference between the liquid limit and the plastic limit. So plasticity index, difference between liquid limit and plastic limit. So it's this distance right here. This is the PI. And then another one, and this is the primary one. This is you need to know that one by heart. Okay, what is the plasticity index? The liquidity index, you don't need to know it by heart. I sub L. This is the so-called the liquidity index. Liquidity. Not used as much as the other one, and it's equal to the natural water content minus the plastic limit water content divided by the plastic limit minus the liquid limit, or if you prefer, W minus WP divided by the plasticity index. Okay, that's the liquidity index. And you'll have to calculate those things in the lab when you do that one. Let's talk a little bit about the applications of these, and why are those things so useful to us. First of all, I'm on page 55 here. Oops. Page 55. When the PI increases, the particle sizes decrease. So high PI, very small particle. We talked about Montmorillonite. PI could be over 100 for Montmorillonite. PI of carolinite, much lower, 20 maybe. So the PI increases as the particle size decreases. If the PI is high, material more difficult to compact. You know, if you have a PI of 30, 40, very difficult to compact. Not a good idea to use that kind of material for road base, for example. It doesn't drain well. This is why the Texas Department of Transportation, for example, has a limit of 15 on the PI. You cannot use a material that has a PI, a plasticity index higher than 15 for road base, backfill, and so on. It's also when the PI increases, the shrink swell potential increases. Okay? And I told you that the range of PI varies from, say, 10, 20 for clays, all the way up to over 100. And so if you have a high PI, you're going to have like something over 50, let's say, you're going to have some significant shrink swell potential and all the associated troubles with foundation engineering, for example. When I bought my house, when I bought the land for my house back in 1989, I checked, you know, I went to, took a hand auger and brought some samples to the lab, and then bang, 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 roly-poly and stuff, did the Atterberg limits, and found out that the PI was 75. And I said, oh my goodness, I better be careful with the foundation. So I beefed up the foundation, and knock on wood, no problem so far, 30 years later, so that's good news. And you know, I could have moved away from them and find another place, but it was perfect. You know, I had the direction for the tennis court, and it was a beautiful lot, not very expensive too. So I said, that's it. I'll make sure I work with this. So shrink swell potential as the PI goes up. The PI, when the PI goes down, when the PI goes down, you have better drainage. Better drainage potential. What else did I put in there? So that you can use it, more likely to use for pavements, for retaining wall, backfill. And so on. As the PI increases, the friction between particles decreases. So for example, the coefficient of friction between Montmorillonite particles with very high PI will be much lower than the coefficient of friction between sand or gravel particles. So that's another indication. So you can see all those things that give you a clue, several clues about what to use a material for, what to be careful with, and all this on the basis of tests that cost $50. And again, you want to be famous, you want to be rich, develop something that's simple, inexpensive, and very useful. And that's what Atterberg managed. One of the other things that's very important that came out of the Atterberg limits is the classification of fine-grained soils. And the classification chart is another very important application of the Atterberg limits. This chart was developed a long time ago. Casagrande had a lot to do with it. And on the vertical axis, you have the plasticity index, and on the horizontal axis, you have the liquid limit. So the liquid limit goes from 0 to 100, I think. I mean, it can go higher than 100. And the PI goes from 0 to 70. It's on page 55 of the book. And you will see that, so around 50 here, you have a boundary. And there's the chart looks something like this. And it goes like that. Above the blue line are the clays. Below the blue line are the silts. Below 50 liquid limit are the clays and silts with low plasticity. Above the 50 liquid limit boundary are the high silts and clay material. So here we're going to have high plasticity, low plasticity, low plasticity clays. Here we're going to have high plasticity clays. Here we're going to have high plasticity silts. And here we're going to have low plasticity silts. And here in that zone, we can't decide, so we got to use, it's a boundary, and then we'll see more about this when we deal with the classification. So we now have seen all the elementary tests that it takes to be able to classify the soil. We've seen, the phase diagram, the unit weights, the water content, the void ratio. We've seen the grain size distribution curve with the coefficient of uniformity, the coefficient of curvature. We've seen the Atterberg limits with the plasticity index and the liquid limit and the chart. We now have all the elements to be able to classify the soil. And so next time we're going to go through soil classification, and you will see that this is a system that has been agreed upon by the international society. So it's a worldwide accepted way of classifying soil. So whether you're in Japan, England, South America, we talk the same language. So it's a remarkable achievement, and we'll cover that next time. So I'll see you next time.